but. Does anybody have any questions about the homework material you've covered? I posted, I believe, the homework and the solutions for the problems I gave you based on the discussions, right? Did everybody get those? All right. So, we're starting a little early, but that's okay. Any questions? Yes, sir.
I'm not asking you to solve it, but could you give us a little rundown how we're supposed to do 2.47?
Yeah. Sure. Give me 1 second. Was this part of the homework? 247? Okay. All right, well, I'll put it up, all right? I want to do this one. And by the way, these problems, once you see it, they'll be trivial. Until you do, you'll be scratching your head. But that's the way this stuff works. All right, so 247. These are all 1K resistors. The K is 1,000, so there are 1,000 ohms. This is the problem. Here's the question. What's I naught? Now, here I told you use Kirchhoff's current. Remember we went through Kirchhoff's current law, right? Whatever flows into a junction flows out, right? That was the standard law. But we did things in order to solve it, and these are things you have to know. So if you're going to use Kirchhoff's current law, and you don't have to, but it lends itself to the solution of this problem. The first thing you do is put a ground in. That's the 0 volt point. Do you all remember me saying that? Right? Everything's going to, all the voltages in the circuit will be measured with that as the reference. And can you all see it back there? All right, if you can't, you yell. Remember, K is 1,000, so these are 1,000 ohms. And I don't put the ohm symbol there, it's assumed, okay? All right, now, the next thing is unknown voltages. Well, that's 0. You see how this is a T everywhere in there, and that line has to be a voltage, but it's unknown. It's called a node voltage. I'll just call it V1. You can call it VA. You have to identify it with some symbol. Yes, miss?
The 2 and the 4, are those milliamps?
Yeah.
Okay.
This is in your homework, by the way. It should be. You all able to view the homework on OneNote? Okay. Yeah.
Could you do us a solid and put that link inside of like an announcement in the Canvas?
What's that?
Like the shared point, the OneNote link. Could you put that on like an announcement in your?
He's going to send it to me, right?
Oh.
Right. It's in Canvas. He said, right?
He's asking about the homework link.
Oh, homework. It should be on OneNote.
Because you put it in an email, I think.
It's not on Canvas. Outlook.
No, not Canvas. OneNote.
Outlook won't let you navigate. That's probably the problem.
They're wanting.
Or to get to
No. It's on OneNote, isn't
No,
it?
we know.
Yeah. If you have one, you're able to go to OneNote.
The issue is
Yeah,
it's hard to navigate.
Hold on for a second. Let me make sure I know where the problem is. How many can view this on OneNote? All right, the entire homework, right? All right, so if you have problems, view it on OneNote.
They're asking for you to take the link that you put in the email and put it in a Canvas announcement.
Because the link is not clickable, since it's the subject of the email.
Yeah. The link that's in the email, just put it in a Canvas announcement.
Oh,
is
to
what
go
they're
to
asking.
OneNote.
Yes, to go to
Okay.
OneNote.
I'll do that. Sorry, I misunderstood.
All good.
All right. Would you remind me out of his class, please? And whoever's having trouble, just see me after class. I'll make absolutely sure you've got it down, okay? All right. Now, back to this thing. You see how I'm gonna call this V1? Is everybody okay with that? Now, it's up to you. I always use V sub 1, V sub 2. Some people have V sub A, V sub B. Doesn't matter, as long as it defines some unknown voltage. Now, here's another unknown voltage, right? We'll call that V2. Do you all see it there? How many do? Make sure. Okay, good. Now, everything else I see, right? Here's what I like to do. Whenever possible, simplify before you solve. That's sort of it's the golden rule of engineering. We're supposed to make things simple if we can before we solve them. How many see some things we can simplify? Yeah.
So you can third series on the left, right?
Y'all see the series resistances? There's 1K in series with 1K. Y'all see it? What can we replace it with? 2K, right? And I'm gonna do it this way. $2K, and I'll even put the ohm symbol if you like. All right, keep going. You're on fire now. Where else?
On the opposite side, you do the same thing.
Y'all see you have 1K and 1K in series over there? Just 2K. Y'all agree with that? Simplify. Now, I know this is the current I want, but it doesn't matter if it's 2 resistors or 1 because it's the same current, correct? All right, now we want to solve that. The way I told you to solve these things is use Kirchhoff's current law. Whatever goes into stays into or comes out. Whatever goes in comes out is the way I like to write it. And in fluid dynamics, they probably have other things that they say like this, but whatever goes in comes out of that point, the node. So now you label currents, and this is up to you entirely. Anything going from top to bottom, I draw the arrow this way, and I'll just call that I1. Doesn't matter what you call it. That's an unknown current. Do you agree? I'll call this I2. I've already got the 2 milliamp and the 4 milliamp here, and that's I0, so I've got all my currents labeled, don't I? You agree, class? Now you asked about this. This is a great, great question because it leads into what I was going to talk about anyway. All right, now to solve this, you start at each of these nodes and you sum currents, okay? So I'm going to start at this first node, and I'm going to say, well, what flows into that? Does anything flow into that thing? Can you all see this node right here? Nothing flows in, does it? Everything flows out. So I got I1 plus 2 milliamps, right? Plus I2 equals 0. That's fine. Here's what I'm going to do. You don't have to do it this way. That's a constant. I'm going to put that on the other side. You all see that? So I'm just going to take that and make it minus 2 milliamps. Add minus 2 milliamps to both sides, okay? Now, after that, the currents I'm going to define in terms of the unknown voltages. Do you all follow me? This is what we did last time, wasn't it? So here, when I look at I1, right here, what is I1? Well, it's the voltage on the side the current's entering minus the voltage on the side the current's leaving divided by the resistance. Do you all agree with that? Give me a show of hands if you do. All right? Okay. So what's the voltage here? V1. It's unknown, but it's V1. What's the voltage here? That's the reason we put a ground in. We don't have to write that 0 down. It gets rid of some effort, right? So it's going to be V1 over 2K. Do you all see that? Over 2K plus, can anybody tell me what I2 is?
It would be V1 over 1K.
V1 minus V2.
Minus V2.
Yeah. So you had the right idea. It's V1 minus V2 over 1K, right? And actually, if you would have said minus V2 over 1K, you would have been right. You might have been going there.
That's what I was trying to get to.
But I like to put the difference in voltage by itself divided by the resistance. Got me? Equal to minus 2 milliamps. Everybody follow me on that?
How do
That-
you subtract
Remember what we always said, it's the voltage difference. If we talk about a resistor, right? R, if you had a plus to minus voltage sum VR here, but there was a V1 there and a V2 here, then VR is defined, because it's plus to minus, as V1 minus V2. Remember, the V1 and V2 are measured with respect to the ground potential. You follow me on that? So always it's the voltage difference across the resistor where you're referencing a point, right? The ground. So it's V1 minus V2. That is the difference in voltage across there. Now I'm going to say this. You can see we've got two unknowns in this equation. I like to make these things simple. So the first thing I'm going to do, you see how K is 1,000, right? Milli is 1 over 1,000, right? So frankly, every one of these terms is divided by 1,000. Do you agree with that? So I multiply both sides by K or by 1,000 and get rid of this stuff. That gets rid of the milli and the K. Y'all follow me? There's nothing tricky here. And then I go ahead and I try to make, I don't like fractions. You don't have to do it this way. This is me. I multiply everything by 2. All right? So that puts a 2 here, makes this minus 4. And then after that, I organize things where I have the coefficients of V1, coefficients of V2 equal to constants. We're going to go for a matrix solution. So I have V1 plus 2V1, or 3V1, minus 2V1, or V2, pardon me, minus 2V2, equal to minus 4. Y'all see that? And I call that my first equation. And again, I started by applying the ground, defining the unknown voltages, and then defining the currents, and setting all the currents into each of these nodes equal to whatever comes out of them. Yes, sir?
What was your reference point when you described the resistor from positive to minus? How did you know?
Well, remember, current is defined as, the current is defined as the voltage difference plus to minus where the current is entering the plus terminal, right?
So
Divide.
so it's the direction of I2 that let you know it was.
No, it has, yeah, exactly, because this has to be positive, that has to be minus. Current enters the positive terminal of resistor and leaves the negative. Y'all follow me on that? It's a notation. You have to be clear about this in your mind. All right, and if you work several of these problems, a bunch of these problems, it'll become evident. Now, that's the first equation. The second equation is going to be for the second node, isn't it? All right, just in terms of current, what goes into this second node? I2 and 4 milliamps. Do you all see it? And can you all see what comes out? Just I0, isn't it? Isn't that right? So you have I2 plus 4 milliamps is equal to I0. Agreed? I'm doing it slow for a reason. There may be little things I don't know you don't see. All right? And it can be subtleties that I can't pick up on. Especially because everybody's wearing a mask. Almost. All right. So, now what? What is I2? Anybody respond? No, somebody new. What is I2? Want to give it to me? Next, behind you. You want to give it to me with a laptop? No? You? Yeah. Why not you? Sure. The guy turning. Yeah. Yeah.
Okay.
No, not you. Him. Yeah. I've been doing that all day too. What is I2?
What's I2? I2 would be.
Look up here.
That would be 2 milliamps. Or,
Can you see that I2? Can you read my writing?
V1 minus V2.
oh.
It's going to be V1 minus V2 over 1K, all right? Don't feel like a fool. Believe me, I feel like a fool every day. My wife reminds me over and over again what an idiot I am. All right, but I'm telling you, there are no dumb questions. I'm only trying to get you to think about this. That's the reason I'm calling it. I want you to pay attention. All right, so it's going to be V1 minus V2 over 1K, right? That's plus 4 milliamps equal to I naught. Somebody else, what's I naught? Go ahead, you wanted to answer.
So would I not just be, IO divided by 2K?
Well, I naught is the current we want. Isn't it V2 over 2K?
I'm sorry, I meant to say V2.
It's okay. You all right with that, everyone? So it's V2 over 2K. Everybody okay with that? Now, and again, this is me. Anybody gonna take a guess what I'm gonna do next?
Eliminate the K, the M, and the K.
Simplify. What I'm gonna do is multiply by the whole thing by 1,000 to get rid of that 1 over 1,000. So I get rid of the K here, the milli goes away, right? Get rid of the K here. Y'all with me? Next. Anybody? Yeah, and that's me. You don't have to do it that way. I do it that way to make it easy. So I multiply everything by 2. I get 8. And then I get 2 here. Finally, I'm going to organize everything, right? I want everything equal to a constant. First, the coefficient of V1 is 2V1. You can check me. And the coefficient of V2 is what? Minus 3V2? And that's equal to minus 8. Do you agree with that, everyone? Check me on that, right? I didn't do anything fancy. I just organized it that way. Why did I organize it that way? Anybody want to take a guess? This is my second equation. It looks like something that you guys in ME and Aero, probably in industrial, do all the time. You solve matrix equations, don't you? Sure you do, yeah.
So why is it V1 minus V2 if the current, wait, never mind, sorry.
This is just an equation that describes what's going on. It isn't the actual I1 equations. All right, so now what I'm going to do is this. I first put the coefficient matrix in front of the column vector V1, V2. So I'm going to have, this is my first equation. I have 3 minus 2, then 2 minus 3, then V1, V2 equal to minus 4 and minus 8. You agree with that? Now thank God for calculators. I used to do this with Kramer's rule. About 10 years ago, I would do this longhand with Kramer's rule. If you remember, you took linear algebra, right? Remember old Kramer's rule? Why bother with it when you got a calculator? What? You taking linear? You got a calculator? You've taken linear. All right, now I mean there's TI-83s, TI-84s, TI-89s, and TI-93, there's Inspiron, I think. And I use an HP from the 1990s. My HP does everything your TI's does, but it's not as fancy. And you guys have symbolic solutions. The calculators these days do everything. They really do. You can't use your phone on a test, but you can use any of the calculators that I've rattled off. So, if you got a calculator, you can solve this for V1 and V2 pretty quickly, right? You want to solve it for me?
I got 0.8 and 3.6.
Hold it. For V1, you got what?
0.8,
And V2?
3.2.
I'm going to ask anybody confirm that.
Putting it in now.
This is a good thing for you to do. Bring your calculators, do the problems when I mention it. Because that way when a test comes or a quiz, you won't be fumbling around all thumbs. And if there's something you don't know, then you'll know it right there. I always tell people to bring their, especially when you get into complex numbers, you're going to see there's all sorts of things you have to know that you don't know when we get into the real and imaginary parts of the magnitude magnitude.
I got the same thing.
How many got the same thing? I got 2. Anybody else? If you don't have your calculator, so be it, but I encourage you to do it. I see people working on the calculators right now. Try it. And I'll tell you why. Because some people find out where they're making mistakes right now. I myself hate when I punch something in wrong. I know what I'm doing, but I'm in a hurry, or I'm not being attentive to that, and it irritates me. I have a cardinal rule that when I do these things, here's what I do. I circle minuses. This is for money, especially if I'm consulting or something like that, doing a journal paper. I circle the minuses because my eyes get weak, especially late at night. And I don't see them, so they look like scratches, so I circle them. And the other thing I do, anytime I can eliminate now here's what I do normally. I'd multiply the top row by -1, so I'd have minus and then 2 positives. There's only 1 negative to worry about. Doing the same down here, but I didn't on this one. All right, if they're all negative, I just get rid of the negatives. Y'all with me? Y'all got, how many got that now? I mean, the same answer. I know you did. You did it. Didn't, who else? You did? Nope, you guys didn't get the same answer?
I'm getting the same answer so far.
All right. It should be a quick thing when you get your calculators. You enter that's this matrix right here. Then you enter, this is called the A matrix. This is the form AX right here equals B, and X is just B times A to the -1. I'm not sure if your calculators do it that way, but that's basically it. It's a square matrix, right?
That one has a matrix solver as well.
It's a 2 by 2. Check your matrix math on it. All right, we're going to continue. Did that answer your question? Oh, wait, we want a current. We got the unknown voltage V2, but how do we get the current I0? Hold it. How do we get the current I0? That's all we want. This is I0, right? What is it? Yeah, it's V2 minus 0, isn't it? It's 0 on the other side, so it's just V2 over 2K. So the current I0, check the answers, is simply V2 over 2K. So it's going to be if this is right, 3.2 over 2,000, and that would be in amps. Can you tell me what that is? That's 1.6 milliamps, right?
Yeah.
Yep.
Okay, is that the answer in the book? Can you tell me? I bet it is. You have the solution, I posted the solutions to this one. You can check it, I'm pretty sure it is, okay? All right, that's a great problem, and it answered it did things I was gonna go over anyway. Any other questions about the homework before I continue? All right, make sure you keep up with this, because this stuff will really bite you if you don't, really come at you hard. Because your book will not go into the level I'm going in. Yeah.
How you designate the I1 and I2?
It's arbitrary. You can have it going this way, you could have it going up. I always go from top to bottom, from left to right, unless there's a good reason not to. In other words, if I had a voltage source over here, and an unknown voltage here, I might have it going that way, but it doesn't matter, because remember, the direction of current only tells you one thing. It tells you how you're going to subtract the voltages across that resistor, right?
So also V1 and V2, V2 is a source voltage?
Not a source, it's a node voltage, right? A source voltage would be something that's defined and can't change, like a 3-volt battery, right? Okay, now pay attention to the next part. Y'all good with this class? Any questions before I move on? How many see this right here? It will be the same always. When you come to problems, any kind of problem like this, there are a few things you have to know. All right. Next, we're going to talk about something when there's a voltage source between 2 node points. This is called a supernode. All right. And it would be like this. If I had something where I had, say, a current like so, call it I1, then I had a resistance R1, a resistance R2, A current I2, a resistance R2, R3, and a ground like this. We're going to use nodal analysis. You see how there's a voltage between two node points? You all see that? It's not a, right? It's not a resistance. You all follow me on that? Well, the way you deal with this is called a supernode, when there's a voltage between two node voltages. Now, this is 0 volts, right? I put the ground on automatically. You all see that right there? Keep watching. Now, right here, there's an unknown voltage V1 with respect to ground. Do you all agree with that? Right? We don't know what it is. This Vs is across these 2 points. It's not with respect to ground. You all see that? Then we have an unknown voltage here. We can call that V2. Now, here's the thing. When you have a voltage between two node points, it's called a supernode for one reason. Because I don't know the current through that, no matter what equation I write. Do you all follow me? It's a voltage. There's no resistance across it. Do you all see that? So what we do is this. We draw a big circle around it and every connection to it. And everything flowing through that circle has to be flowing out of that circle. It's the same thing as Kirchhoff's law for a node. Whatever flows into flows out. As a matter of fact, in the general form of these laws is if you have any planar geometry with a circuit wiring diagram, if you make any circle there, everything flowing into that circle, all the currents flowing in have to be flowing out. Do you follow me? So here what we do is expand it from a single node to several nodes. It's still legit. And we say anything flowing in there is flowing out of there. Now, we go ahead and assign currents. I've already got I1 right here, right? That is I1. That's defined by that source. That's a current source, by the way. I don't know if I said that explicitly. I had the batteries there, voltage sources. Remember that? Whenever you get a circle like this and they have an I here, that's a defined current source. The value is given. It doesn't matter about the voltage. You follow me? That's called a current source. Here, that current's defined, right? But this current isn't defined, so I'll just call that I2. Y'all with me? Now remember, these two are going in or out of this circle. They're crossing this purple line. Yes, sir?
Don't you already have I2 over here?
Oh, gosh. Yeah, let me call this, I'll call that I2, and what I'll do, I'll call this, no, I'm going to call this, how about we do this? I'll call this IA, my bad. And call this IB. That way I can call this IA here, and I'll call this I1. And then I'll call this I2. I'm sorry for the confusion. Thank you for pointing it out. Are you with me? I'm just labeling things. These are sources, IA and IB. They are defined. I could put 5 milliamps, 1 milliamp, whatever they are. That's a defined source. It cannot change its value. Here's a defined voltage, Vs. Those resistors are defined. The thing that we don't know is the value of I1, I2. We know IB, but I want you to notice this. I didn't define current in and out of there. You all see that? I just defined currents that are crossing that purple line. You all see that, class? Now, pay attention to this part. When I write this equation, I'm going to say whatever flows in flows out. So what flows in? IA flows in, right? You agree with me? Does anything else flow in? That doesn't, that doesn't, that doesn't. That's the only thing there is. Do you all see that?
Yes, sir.
So everything that's flowing in is flowing out. So I set that equal to I1, right? Then I set it equal to IB. And I set it equal to I2. Now, I've made the statement IA and IB are defined, right? Right, those are sources. So what I'm gonna do, just to keep everything straight in my head, I'll take the IB to this side. Okay? And now I'm gonna make a statement right here, that VS is equal to V1 minus V2. Do you see how that's gotta be? Take a look at this. If we're at VS, right? Right here, there's VS with respect to ground. We go through the source, we increase, I'm sorry, we're at V2, pardon me. And we go through this source, we increase by VS. So V1 would be V2 plus VS. Do you all see that? Or really the difference from the plus to minus is just V1 minus V2. Do you all see that? So that can be your first equation. Now your second equation is just exchanging, remember IA and IB are known. And now what's I1 based on that drawing? Remember, it's node voltage we're worried about. Anybody? What's this current I1? Take a look. Go ahead.
Is it VS and the R?
Well, it's, you're reading this, that's V1, isn't it? It's V1 divided by R2, right? Because VS is this voltage. Do you all see that? You're far back here. It's V1 divided by R2. And what's I2 here? Anyone? That voltage, right? That's the node voltage, right? V2 divided by
R3.
R3. Because it's V2 minus 0, we don't write the 0, right? So it's just V2 divided by R3. And now, if you look at this, I have two unknowns here, two unknowns here. You can solve that. Now, I left it in terms of unknowns. I didn't put in the values. How many see that? You have two unknowns and two equations. You've got to be able to get a solution that you need, right? Okay. Yes.
So that VS means not the V sources, right? It's just.
It would have a value of 4 volts, 3 volts. It is a known quantity. VS is known. It would be like a voltage on a battery.
If it is like between the V1 and V2, we know V1, V2 are nodes. So the VS is called supernodes?
The VS causes the supernode. Whenever a voltage is between two unknown voltage points, they're called nodes, it is a supernode. What it really boils down to, if you see a battery in a circuit where one of these things isn't on ground, one of the sides isn't going to ground, you got a supernode. That's what it is. And I'll give you problems with this.
So that circle is called.
Thank you.
So that circle
bomb.
is a supernode.
Yeah, the supernode means instead of just having a single node point, we call it a supernode because it's really two node points. But we don't even worry about the current flow in there. We just put a big circle and everything flowing through that circle is flowing out of that circle. And we encase the actual voltage source. You follow me on that? How many do? Okay, I'm going to give you problems on that, and that way it'll flesh out and you'll be okay. But I'm going to warn you about one thing. Don't get real comfortable. Oh, I see it. I don't need to do the problems. I promise you there'll be little things you don't see that'll confuse you if you don't do them. I get a look from people like, I got a question, boy. Boy, do I have a question. What would you ask on a test? That's what I get all the time. Would you ask anything like that? Want to do one? Why not? 251 is a great problem. And you have it, I didn't assign it. The reason is, it's got everything I'm talking about and more.
So you'd say 2.51 is a good test question?
No, I say it's a great problem. But I sure can doctor that up and make it a great one. I don't know if, where I heard this, but I know it's true, that after a principle is stated, any kind of a, like F equal MA, immediately afterwards, there should be a series of examples that you apply the law you've been exposed to, so you get a good feel for it. So 2.51 is perfect. What a great test question. Somebody told me a lot of people in here may be going to the Penn State game. I did my undergraduate and graduate work at Penn State. And I don't know where you're gonna stay. Because I'll tell you, that town is not Hotel City. So if you're a fraternity or sorority, you got a chance. Otherwise, have fun driving to Philadelphia after the game. If you think it's hard getting a hotel down here during a football game, wait till you go to Penn State. It's not off a major highway. How many are going, by the way? I've been told a lot of people. Oh, that ain't a lot. Well, remember what I told you. If you don't know a place where you're gonna stay, don't think you're gonna find one.
I got one.
Okay, now, and again, if you got a network of people, good luck, but I know in the past, people just take off the games, oh, we'll find a place. Good luck. You'll be driving 4 or 5 hours to find a place. Oh, sorry, I didn't put those values down. 1K, they're all 1K, thank God. Oh, I love that value. All right, so here's, I even put the ground in for you. All right, and what do they actually want? Oh, they want this voltage. How nice. They want this voltage. Now, this is what I always tell people. Don't ever worry about what they ask for. That's not, your primary concern is finding unknown voltages. We can find this voltage in a heartbeat once we find the unknown voltages. You all see we're going to use nodal analysis for this one. Now, first I'm going to go ahead and label the voltages at that are unknown at the node points. I'm going to call that V1. You all see how that is a node. There's a voltage there that's not zero, right? Everybody see that?
Yes,
Okay.
sir.
Now, keep going. Here's another unknown voltage right here, right? That's V2. It's like in a pipe, it's a pressure value at that pipe head. There's two unknown voltages. Yeah, V0 is unknown, but how many see that if we have V2, we have V0? Give me a show of hands. Yeah, sure. That's voltage division, right? I got V2, I got two series resistances, right? Whatever V2 is, V0 is simply 1K over 2K times V2, isn't it? Right? It's just 1/2, isn't it that? How many see that? If you don't, I'll show you, but it'll become very evident to you as you do these problems. All right, now, what are the two equations? First, get V1 and V2 in terms of 12. What is it, class? Anyone?
12 is equal to.
How about we do this first? V2 minus V1 is 12. Do you agree with that? The one on the positive side minus the one on the negative is equal to 12. Do y'all see that, class? That's what you're going for. I like doing it this way because it'll help, trust me. Now, the next thing I got to do is assign unknown currents, right? And I label them the way I like them. Well, that one's labeled, so no problem there. I don't know this one, so I'll just call that I1. Right? I don't know that one. I can call that I2. Now, can you all see that these two I could just make a single resistance? But since I want V0, I'll just label this I3. And I know that the single resistance value is 2K. How many see that? Right? All right. Now, y'all see there's a voltage source between two nodes, isn't there? So what do?
Supernode. Circle it.
There you go. Right? Everything going through that purple circle is coming out of that purple circle in terms of current. You all see that, class? All right. So now, and you guys will get good, you'll just fly through these problems after a while because it's very obvious once you look at it. All right, so what when I did that, take a look at the currents flowing in. I like to do it this way. You see the 2 milliamp flows in, it doesn't? So I got 2 milliamps flowing in. All right, what else flows in? Anything? Doesn't look like it. Everything else is flowing out, isn't it, class? And what's flowing out? I1's flowing out. I2 is flowing out, right? And I3 is flowing out. Can you all see that? By the way, in the back, you guys can see, right? If you can't, yell, please, because I mean, these are odd times for me. First, masks are just not my thing. Second, I mean, I'm not sure where we're going to be in a week or two. I really am not. I'm trying to do the best I can with what I got to work with. So now let's go ahead and replace the I's with the V's, because that's really what we're at, aren't we? So what I'm going to do is put the 2 milliamps over on this side. And now, what is I1 with respect to the unknown voltages, anyone?
V1 over 1K?
Yep, V1 over 1K. And what is I2?
V2 over 1K.
Sure. V2 over 1K. And what is I3? V2, just V2 over 2K. See how that goes to ground right there? Don't worry about V0. We could write another equation, but it'd be stupid, right? I mean, we don't really care about that voltage. Whoever said that, I'm glad you did. We care about this voltage, and you see how this has a path right to ground. Do you all see that, class?
Yes, sir.
So we just take V2 divided by 2K. I mean, yeah, V2 plus V2 over 2K is equal to 2 milliamps. We could write another equation where I3 comes in equal I3 coming out. And I3 would be V2 minus V0 over 1K here equals V0 over 1K here, but then it boils down to V0 is just V2 over 2. All right, so we don't do that. We go for the unknown voltage V2. You all see this, class? Now, at this point, I think you know how to handle that. We've got that equation, this equation. You see how we have two equations, two unknowns? Right? We only have V1, V2. There and there. There's the one right below the 2.51 and that one. How many feel they can solve that? All right, everybody in here should feel very comfortable solving two equations with two unknowns in this class, where they're not some kind of, interpolation because it's a nonlinear equation. These are very simple linear system problems, okay? So please make sure you can solve this quickly and get the answer using matrix math. And what I would do is just multiply both sides right off the bat by by the K here, so I get rid of the milli in K. And then after that, multiply everything by 2. So I'd have 2V1 here, 2V2, and 1V2, so I'd have 2V1 plus 3V2, right, would be equal to 4 on that side. Agreed? And then you would have the other equation there. You set up a nice matrix and solve it. How many see this, class? Yeah.
So does it matter that over here it's equal to 12 volts and over here it's equal to amps? Does that
Well,
change anything?
remember, once we multiply by K ohms, is really what I should say. When I multiply by K ohms, then I have volts. That's volts. Right? Because the K, I say multiply by K, it's K ohms. Ohms times amps is volts. Okay. Goes away. Anyway.
So it's 2V1 plus 3V2 equals 4 volts. And when you finish simplifying all that,
here it's going to be what? 2V1 plus 3V2 would be 4. Yeah, you're right.
4 volts.
Yes. The units have to work. And over there it's volts too, so you make them a nice matrix, solve it, okay? All right, hang with, yes. Oh, I thought somebody was about to ask a question. All right, now that is, in a nutshell, that is probably the most important way to solve problems that are circuits problems with unknown voltages, all right? And even with a supernode. Now there are other methods I'm going to expose you to. If you've had another class or other things where they didn't, don't worry, but I've taught this course many, many years. I know the person who I know Dave Irwin, who wrote the books on circuits, he's upstairs, and I know the importance of being able to solve circuit problems a number of ways for simplicity. The next thing I'm going to talk about, this is really Kirchhoff's current law applied to circuit problems. We really define things in terms of unknown currents, but we actually solve for the voltages, don't we? And then when we solve for this voltage, can everybody see once we have V2, V0 is just V2 over 2, isn't it, class? Because there's two resistors that are identical in value in series, and we want the voltage over one of them. It's exactly half, isn't it, class? Okay. Next thing I'm going to do is talk, and I'll give you more problems on this. I really appreciate you doing them. Now I'm going to talk about something called loop or mesh analysis. How many have heard of loop or mesh analysis? All right, it is a dual to this. It has some advantages, but it's just another way. And this is applying Kirchhoff's voltage law. The sum of the voltages around any closed loop are zero. So here, I go ahead and I'm going to give you the standard setup. So make that a voltage V1, some R1, some R2, some R3, and some voltage V2. These things are source voltages. They are defined. Now, I've got unknown resistances. And the way you would solve this, based on what you know, is you would put a ground here, right? Put that at 0 volts, then you would have one unknown voltage, and you would define your currents into and out of, and say whatever goes into the node would come out of the node. That's the way you do it if you were using Kirchhoff's current law or nodal analysis. It's what we just gone over, right? But when we talk about mesh or loop analysis, what we do is this. We assign what are called mesh currents. So we put a little current in here that's circulating in that loop, and we put a little current here in this sub-mesh circulating in that loop. Now you're just going to have to go with me for a second. By the way, this probably has a direct relationship to what you learn in fluids for incompressible fluids. I don't know if it's hydraulics or what do you call the course anymore. Anyway, for this, we go ahead and we assign voltages. There's going to be a voltage drop here, VR1, and a voltage drop here, VR2. Now, I want you to watch what I'm about to do, please. So now, if I pick any point in this circuit, and I go around any closed loop, I know the voltages will sum to 0. Do y'all follow me? Doesn't matter if I go this way. You got to end up where you started from for a closed loop. Start here, go here. Doesn't matter if I start here and go here. It'll still sum to 0. Got me on that? So I'm going to start here and I'm going to sum the voltages. From here to here, it's a voltage increase in V1, is it? Then there's a voltage decrease, but now I'm going to not put VR1. I could put minus VR1 and then minus VR2 equals 0, couldn't I? But I'm going to define the voltage VR1 in terms of the unknown current. And that would be minus R1 times I1. Take a look at that. Do you all agree with that? Make sure you do in the back especially, because I worry about the people way back there. Y'all see what I'm doing? Now here's the tricky part. The voltage drop here is the net current flowing down, which would be I1 minus I2. You see how both of those currents have a component in the center resistor. Do y'all see that? So it's the net current flowing down times R2. So it's minus R2 times the net current flowing down, which would be I1 minus I2, and all this equals 0. Do you all see what I've done? How many do? Remember, the trick is making sure that net current flowing down. We got I1 going that way, I2 going up right there, right? So we have to take the net current would be I1 minus I2. Do you all see that, class? All right. Now, we keep going. That's the first equation. Now, you can see I'm going to simplify it, right? Y'all with me? I'm going to go ahead, I'll multiply out, and I'll gather the coefficients of I1, and I'll gather the coefficients of I2, and I'll put any constants on the other side. You with me on that? Now we go through the second loop right here. And I always start in the lower left-hand corner, and I go around the circle, but I take everything as a voltage drop, meaning this. And I hope you catch it. Now I'm going to erase that polarity here. Since I said everything I want is a voltage drop or a loss, I want this voltage here, and that one's already predefined. So when I start here at this lower left-hand corner, I'm going to have a minus R2, and now it's the net current flowing up. Do you all see that? Take a look. I want the voltage drop plus the minus, so I got to take the current flowing that way, and that would be I2 minus I1. See how it reverses now? So it's going to be I2 minus I1. All right. What about here? What's the voltage drop here? Can you all read that? Minus R3
I2.
times, right. What about here? What happens? From here to here, it's a voltage drop of, right, now minus V2 equals 0. I'm literally a minute over, but bear with me. Y'all see what I can do is take V2, which is known to the other side, and then I can organize this where I have coefficients of I1 and I2. Do y'all see that? Now I would have a 2x2 matrix again, wouldn't I? And guess what? That's what your calculators were born to do. They'll knock these out in a heartbeat once you get used to them. I'll give you some problems, and on Monday we'll talk about them. Please bring your calculators to class and do what I say so you'll be ready for the quizzes. Next Friday, unless something changes, we're going to get a quiz, and it'll be a pretty thorough quiz. Okay. I didn't want to do it today because there's too much going on.